Hi everyone, welcome to today's GCSE Chemistry session. So it's part of the MyTutor online school. Today we'll be looking at materials and the Haber process, so carrying on from where we were looking at alloys and polymers last week. If you haven't met me before, my name is Aman and I've taught all the GCSE online school sessions. I study medicine at King's College London and I've done plenty of lessons with MyTutor. This session will last for 1 hour, from 2 p.m. till 3 p.m. And as usual, if you have any questions at all, please pop them into the chat or the Q&A function and I'll try and answer as we're going along. So let's go on to today's content. So the learning objectives for today, we're going to know and explain how the physical properties of glass and ceramics relate to their uses. Explain the uses of composites, and I just want to emphasize that composites is a purely AQA based topic, so if you're studying Edexcel or OCR you do not need to know about composites. Recognize the uses of nitrogen based fertilizers and understand the Haber process. So we've looked at the Haber process before, but we'll be looking at it in a bit more detail today because it relates to the topic of fertilizers. So before we start, does anyone have any questions at all? If you do, please pop them into the Q&A or the chat box function. As usual, we'll start off with a quiz testing last week's content. So we did alloys and polymers last week. So if you go to Menti and type in the code 694419, you should be able to join the quiz. So if you were here last week, you'll know that we looked at specific alloys, so things like brass and bronze. And we looked at thermosetting and thermosoftening polymers. So if you go on to Menti, we can do a quiz. Yep, someone's asking about the Haber process. It is used to make ammonia. You are correct. Yep, so we'll be looking at that towards the end of today's session. But yes, keep that in mind. So if you want to join the quiz, please do menti.com and the code is 694419. So I'll wait a few moments for a couple more people to join. I hope you've all had lovely weeks. I'm sure lots of you are back at school now, and I'm sure that's very different from when you were there last year. While we're waiting for people to join, I just want to remind you that there are group sessions going on, so small group sessions, which you can join for other GCSE subjects and also A-level topics. So if you go onto the MyTutor website, you can join from there. The other thing is there's always one-to-one tuition, so if you feel like you want a bit more help, please go onto the MyTutor website and you can find more tutors specified to specific subject areas. Okay, let's start the quiz. Great to see so many of you here today as well. Okay. Ooh. Okay. So the first question should be coming up on your screen. So which alloy tends to be used in producing aircrafts? Bronze, brass, duralumin or steel? Which alloy tends to be used in producing aircrafts? Okay, great. So the answer is duralumin. Can anyone type into the chat box function, what is duralumin? What's it made of? Does anyone know or remember from last week? Type into the chat or the Q&A function, what is duralumin made of? Yes, it's got copper in it. Good. What's the main metal? Good. Aluminium. So aluminium and copper. Excellent. Well done. From which 4 elements is stainless steel made of? So from which 4 elements is stainless steel made of? Is it copper, nickel, tin and gold? Nickel, tin, silver and iron? Iron, carbon, copper and nickel? Or chromium, nickel, iron and carbon? So hopefully you remember what steel is made of. So that should knock a couple out for you if you remember what steel is made of, and then it's about what makes it stainless. Good. Okay, so the answer is chromium, nickel, iron and carbon. So it looks like most of you remembered that steel is iron and carbon, which is excellent, but it's the chromium and nickel that makes it stainless. So not copper, it's chromium and nickel. Any question on that? Because that's quite a common exam question asking about stainless steel, so it's important you know the 4 elements. The way I remember it is always to remember that steel is iron and carbon, and then chromium tends to be used in very few materials, so I always know it's chromium in stainless steel and nickel. Okay. Which of these is a use of low density polyethylene? So last week we looked at high density and low density polyethylene. They have different properties. So if you can remember the different properties, you'll know what the use of a low density polyethylene is. Is it plastic bags, pipes, buckets, or plastic bottles? So 3 of them are uses for high density and 1 is a use for low density polyethylene. Okay, great. So the answer is plastic bags. Well done to everyone that got that correct. So low density polyethylene tends to have a branching structure. And what that means is that the bonds in the polyethylene aren't as strong. And so it tends to have a lot more of a flexible structure and tends to be a lot less hard and tough. Whereas high density polyethylene has a really kind of rigid structure, which gives it a lot more strength. And that's why pipes, buckets, and plastic bottles, which if you think about milk bottles, for example, the plastic that's used in that is a lot tougher than a plastic bag, which is quite flimsy. So plastic bags are made of low density polyethylene, and high density polyethylene is pipes, buckets, and plastic bottles. So well done. Okay, the next question, what stops thermosetting polymers from melting when heating? So we looked at thermosoftening and thermosetting polymers. You had to type the answer in this time. So what stops thermosetting polymers from melting when heated? So there's something in the thermosetting polymer structure that stops them from melting. Does anyone remember? Type in the answer and we'll see if you are correct. Yep, so someone's asking to go back to the first question, so I will do that when we get to the end of the quiz. Okay. Good. Okay, so covalent bonds, yes, cross-links. So the official name is cross-links, but you can call them covalent bonds. They are covalent bonds, and it's those covalent bonds that thermosetting polymers have, which thermosoftening polymers do not. So thermosoftening polymers, because they don't have covalent bonds, you're relying on van der Waals forces or intermolecular forces between the molecules, which means that they're quite easy to overcome. Not a lot of energy is needed, so they melt when heated. Whereas thermosetting polymers have cross-links, which are covalent bonds. And you'll remember covalent bonds are really strong bonds. So we have to add a lot of heat to get them to melt. And that's why often at normal temperatures, they will not melt when heated. You got it wrong, but you said cross-links. That's very strange. I think it's because cross-links are 2 words. So sorry about that. Cross-links are 2 words. That might be why you got it wrong. Okay, well done everyone for taking part in that quiz. It was nice to see so many of you involved. So well done Wolfmeister, you won that one. So someone asked me to go back to the first question, so I will go back. Yeah, it was. Okay, so which alloy tends to be used in producing aircraft? So the person that asked me about this one, I hope it's this question because this was the first question, and it was duralumin. So duralumin is an aluminium alloy. It's made of aluminium and copper, and it tends to be used in aircraft. Bronze and brass tend to be used more in metal structures, and steel has lots of different properties, which we looked at last week. So if you go back to last week's webinar, which is now on YouTube, you can watch that. Okay. So remember I said today we're looking at glass and ceramics, composites, and then the Haber process with regards to fertilizers. So let's start off with glass. So does anyone know what glass is made of? So anyone that's just joined, welcome. So does anyone know what glass is made of? There's 3 raw materials. Good. So someone has said sand. Excellent. So sand is one of the raw materials. Great. So sand, which is silicon dioxide. So SiO2, which is silicon dioxide or sand. That's great. That is one of the raw materials. I should say that the glass I'm talking about right now is soda lime glass. Limestone, excellent. So it's called soda lime glass. So limestone, yes. And limestone is calcium carbonate, which is CaCO3. Good. So limestone. Okay, there's one more. I'll tell you it's a carbonate compound. Does anyone know? So it's a carbonate compound. What's soda? So it's called soda lime glass. So the lime is the limestone. What is soda? Sodium, excellent. So it's sodium carbonate. So soda is kind of a fancy name for salt. So sodium carbonate, so NaCO3. So sodium carbonate, which is your soda. So this is soda lime glass, and why I keep calling it soda lime glass is because there is another type of glass which we'll talk about in just a second. What I want you to understand from this is A, what the raw materials are, and the most important one being sand. So all types of glass have sand in them. And the second thing is how glass is made. So it's a two-step process. We start off by heating our raw materials. So if we're making soda lime glass, silicon dioxide, calcium carbonate, and sodium carbonate, we melt those, heat them up, and then they react together to form molten glass. And then what happens is once they've all reacted and we form molten glass, we cool them down, and that's when the glass solidifies. So it's a two-step process of melting and then cooling. And this picture over here is the structure of glass. And what I want you to notice from that is it's quite irregular. So hopefully you can see it's not a very regular structure at all. And that gives it some of its properties. So does anyone know some of the properties of glass? So if you think about if you've got any windows where you're sitting right now, most windows are made of glass. What are some of the properties of that glass? Milk bottles, some of them can be made from glass. Good, hard and strong, transparent, excellent. What happens if I hit that glass? If I hit it with a hammer or something? What tends to happen? Yeah, brittle, excellent. So someone has said brittle, it's quite fragile. So brittle means that it breaks easily. So glass is a material that tends to break very, very easily. So if you, for example, smash a glass, or if you drop a glass onto the ground, it will tend to break. It's very unlikely that glass will not break. And that is because it's hard and it's strong, but it is brittle. And the reason for that is this structure. So if we have a look at some of the elements in glass, we've got silicon, oxygen, sodium, carbon, calcium, carbon. So there's lots of different elements in there. So who wants to have a stab at guessing what type of bonding occurs in glass? And I'll give you a clue. There are two types of bonding in glass. So you've got some metals in there, some non-metals. What type of bonding do you think occurs? Excellent. So there's covalent bonding occurring. Good. So there's carbon and oxygen in there. It's likely that if they bind together, you will get covalent bonding because they are both non-metals. Okay, what else? Ionic, excellent. So covalent and ionic bonding occurs between metals and non-metals. If you feel unsure about that topic, please go onto YouTube. There's a webinar that we did looking at all of the types of bonds in a lot of detail, which will help with that. But yes, everyone that said covalent and ionic bonding, you are correct. So it tends to form quite an irregular structure, and that makes it fragile and brittle. So although it's got those really strong bonds in there, I'm going to explain this when we go on to ceramics, but when we hit glass, essentially, if you imagine ionic bonding is bonding between a cation, so positive ion, and an anion, a negative ion. If we hit it, that structure gets disrupted. And what might happen is you might end up with two positive ions next to each other. And instead of attracting, they will repel. Or even two negative ions next to each other. And instead of attracting, they will repel. The same with covalent bonding. You can get some repulsion going on when that structure is hit, and that is what causes it to break. So it's when you disrupt that structure and you get repulsion between the ions, you tend to get breakage of that structure. Any questions on soda lime glass? So the key things are what the raw materials are, the two steps which involve melting and cooling. So you can see we have to melt to quite a high temperature, 1500 degrees, and the fact that it's got an irregular structure that makes it brittle when you hit it. Okay. There is another type of glass, which is called borosilicate glass. So borosilicate glass still is made of sand. So all glass is made of sand, but it's got another material in it. So it doesn't have calcium carbonate or sodium carbonate. It's made of boron trioxide. So boron trioxide. Any ideas what properties borosilicate glass might have? And it's okay if not, you probably haven't heard of it before. I definitely hadn't heard of it before I started studying chemistry. So boron trioxide is the other material as well as sand, and it makes borosilicate glass. So I'm going to give you a clue. I want you to imagine a test tube versus the glass in a window. What's the difference between a test tube, or what does a test tube have to withstand compared to the glass in a window? Any ideas? Not pressure. You're close, you're on the right lines. Temperature, excellent. So usually you will do chemical reactions in test tubes, and they can either be exothermic or endothermic. And if they release heat, then they will heat up that test tube, and that test tube has to be able to withstand high temperatures. So one of the key features of borosilicate glass, so remember that's sand and boron trioxide, is that it melts at a really high temperature. And so that means that it tends to be used in ovens. So for example, if there's glass in your oven, you'll notice that it will be borosilicate glass, and also in test tubes, whereas other types of glass will be soda lime glass, which melts at a much lower temperature, so it doesn't withstand heat as much. Okay, excellent. Any questions on that at all, please pop them into the chat or the Q&A function. So we've looked at glass. The next material I want to look at is clay ceramics. So clay ceramics are used quite frequently. So china, so kind of fancy pottery, china, porcelain, baths, toilets, and bricks can be made from clay ceramics. And what's really important to know about clay ceramics is actually what some of their properties are. So wet clay, which you might have seen if you've been on a building site or you've seen some building happen where you're living, tends to be quite slimy. And that means that it can be molded. And then what happens is we heat whatever we've molded to a really high temperature, so 1000 degrees, and then it solidifies. So what we need to understand is, well, why when we add water to it, is it able to be molded, but why when we heat it, is it hard? And that comes down to the bonding in clay ceramics. So I've said here that clay is made of metals and non-metals, so usually aluminium, silicon, oxygen, and potassium. You don't need to know specifically which metals are non-metals. It's just important that you understand what bonding is there. So just like glass, it's got covalent and ionic bonding. So you've got covalent and ionic bonding in there. And what happens is when we add water to clay ceramics, that bonding gets disrupted. And so the structure isn't as tough. So you'll know that ionic and covalent bonds are really hard. You need a lot of energy to be able to overcome them. But when we add water to clay ceramics, essentially they become really moldy, and those bonds are not as strong anymore. And that allows that structure to be able to be made into other things. So that's why we can mold wet clay. But when we heat up that structure, so when we've molded it, we're removing any water from that structure. And when we remove that any water from the structure, you're relying on covalent and ionic bonds in that structure, which makes it really tough. So that's why when we have wet clay, it's moldable, but when we have hard clay, it's essentially been heated to remove any water from it. And just like glass, when we hit that clay, it's really easy to break, and that is because we disrupt the structure of these ionic and covalent bonds, causing repulsion between the ions. Any questions on that? So it's quite similar to glass, but different materials in there. So the water makes it moldable because when we add water to it, it essentially disrupts the ionic and covalent bonds that are there, and basically means that they're not as strong, so you can move it around. So it's all dependent on the bonds not being as strong when we add water in. So it disrupts those bonds, but when we remove the water, the bonds are there again. Any other questions on clay ceramics? So we've had a look at glass and clay ceramics. The other thing to notice is that you can see that the clay ceramics have a very regular structure, so they're in nice, neat layers and lines, whereas if I go back to the glass, you can see it was quite irregular. They're both brittle though, it's just that clay tends to have a more regular structure. Okay, so the next thing then to look at is composites. And as I said, this is an AQA topic, so if you're not doing AQA, you do not need to know about composites. It still might be interesting though, if you do want to learn about it. So we've looked at glass and we've looked at ceramics. So a composite material consists of two or more materials with different properties. So what that means is binding two different materials together. So for example, if we did glass and ceramics, we would form something called a glass ceramic, and that is a composite material. So it's different from, say, an alloy, which is made of two different metals or two different elements bound together, where one is a metal. A composite is two specific materials. And we know that these materials have lots of different elements in them. So specifically, the definition is two different materials, so two or more different materials. And why do we combine them? Well, it produces a material with improved properties. So if we go back to the glass ceramic example, so we know that glass and ceramic are both very brittle. If we hit them, they break really easily. But if we make a composite of glass and ceramic, what happens is, if you imagine, let's say, molds of ceramic. So if we say we've got, let's just say these are different blobs of ceramic molds, and then we add in molten glass. So if we add in molten glass in between, molten means melted glass, it essentially binds those ceramics together. And when it cools and hardens, we end up with a structure called glass ceramic. And what are the properties of these? Well, it stops it being brittle. And the reason for that is that when you hit that structure now, it will only break one thing. So if we hit the ceramic, you will form some kind of break in there, but the whole structure won't break because of the glass in between the ceramic. It almost protects the ceramic. Essentially as well, if you hit the glass, then you might get a crack in the glass, but it won't break the whole structure because you've got glass in between the ceramic. So it protects both the glass and the ceramic. And that's what a composite material does. So you tend to have a binding material, which is known as your matrix. So in the glass ceramic example, the glass is the binding material. It binds pieces of ceramic together. And you have a reinforcement material, which is the other material. So our ceramic here, we added the glass. So the reinforcement was the ceramic, and then we added the glass, which was the matrix or the binding material. And what's really important is there are no exam questions currently out on composites, but predictions suggest that they might ask you to suggest which one would be the matrix and which one would be the reinforcement in a certain material. So it's important to know the difference between them. Any questions on that at all? So you need to know that the matrix is the binder and that the reinforcement is kind of the main material that's being bound together. Okay. So this is a busy slide, but it essentially looks at 4 or so very common composite materials that you may have heard of. So we'll go through them in turn. So let's start off with reinforced concrete. This is the most common one, and if you're going to learn about one, I would definitely learn about reinforced concrete. So reinforced concrete is used in a lot of things like bridges and dams, and we'll look at a couple of pictures in a second. So we've got concrete, and that is our matrix. So that is the binding, and we've got steel rods. So essentially what you have are these steel rods, and then we add concrete, so wet concrete in between, which binds it together. So this binds the steel rods together, and you're going to see that in a picture in just a second. Now, why would we do that? Why would we add steel and concrete together? Well, concrete is a hard composite, so I've said what it's made of here. But what it does is, we know that metals such as steel are really tough and hard. Concrete itself is quite flexible and bendy. So if we want to stop it bending, if we add in that steel, it stops it bending. It makes it resistant to these bending forces. So things like bridges have to be really strong. You don't want them to bend. You want them to be able to withstand high pressures and lots of weight as well. So adding the steel is like the reinforcement, the tough material, and then the concrete in between is hard, and that binds it all together. So you can't just have a bridge made of steel. You also need the binding material, which is the concrete. Any question on that? Because that's the most common kind of composite that you may have heard of, so reinforced concrete. Okay, so the next one is fiberglass. So fiberglass essentially is glass, but we've got polymers in between. So you may remember from when we looked at polymers that polymers tend to have quite a low density, which means that they're quite light, they're quite compact. So when we add polymers into the glass, it stops them breaking. It makes them more flexible, so the glass becomes a lot more flexible. And I'm going to show you a use of fiberglass in a second, which might be quite shocking. And the other thing is they tend to be quite waterproof. So we know glass tends to be waterproof anyway, but adding the polymer in, it makes them more waterproof. And most importantly, they tend to be really light. So the polymer adds in that low density. So if you imagine slabs of glass bound together with polymer, will make them really light and flexible. The next one is carbon fiber reinforced polymer. So does anyone remember a key property of carbon? So graphite and things. What's the key property of carbon? Carbon, graphite. Anyone remember from when we looked at it? So not diamond, diamond doesn't have this property, but yet carbon does. So conducts electricity. Excellent. So if you remember, there tends to be one delocalized electron in carbon, which can conduct electricity. And if you're not sure what I'm talking about, on YouTube, there's a webinar where we look at graphite and carbon and diamond as well. So carbon fiber reinforced polymer, you've got lots of carbon fibers which are bound together with polymers. And again, that's going to make it lightweight, but more importantly, it's going to enhance the conductivity. And also it means that they can be used in materials such as those that need to be tough and lightweight. So we'll be looking at that as well. So things like aeroplanes tend to use carbon fiber reinforced polymers, or the newer aeroplanes do now. It makes them lightweight, and that is obviously good in the air. The final example is chipboard. So wood itself is actually a composite, so it's what we call a natural composite. So most of these composites I'm discussing here are not natural, they're synthetic, or they're made, whereas wood is a natural a natural composite. So wood has in it cellulose fibers. So if you've studied biology, you'll know what cellulose is, but it's essentially what wood is made of. And if you imagine you've got these cellulose fibers, and then binding it together is something called lignin. So there's lignin binding these cellulose fibers together. Now, the way I've drawn it is to show you that these cellulose fibers, which are in the grey, are all in one direction. And that means that wood tends to be strong in one direction. So that also means that in the other direction, wood is not strong. So for example, wood is strong in this direction that I've drawn it in, but it's not strong in this direction. So to get around that, we can add glue as a matrix, so as a binding in between that wood. And what that does is it disrupts the bonding in the wood and allows it to be strong in all directions. So you can see here, it contains randomly arranged wood chips bonded together by glue so that it's strong in all directions. So instead of being arranged in one direction, when we add in the glue, it's randomly arranged so that it's strong in all directions. So I'll just show you some of the uses. So in the top left-hand picture here, the flooring is made of chipboard. So this is wood that is strong in all directions. So instead of adding normal wood in there, we've got in there chipboard, which is strong in all directions, which is what you want for flooring. This is the reinforced steel or reinforced concrete, where you've got your bridges and dams. And here you can see these steel rods, hopefully, and the concrete surrounding it. So that is a composite material. So that is your reinforced concrete here, where you've got steel rods and concrete added around it. This is PPE. So a lot of our nurses and doctors in hospitals at the moment are using personal protective equipment, PPE, which is actually tends to be made of fiberglass. So you can't see the glass in it, but it is there. And what you can see is it's very flexible, it's waterproof, and it's lightweight. So this actually is fiberglass material. So it's got polymer in there as well as glass. And then finally, this is the carbon polymers. So if I go back here, it's the carbon fiber reinforced polymer in aeroplanes, which make them really lightweight and also strong in the air. So someone's asking me to go back to slide 5. So yes, I'm happy to go back to this slide. So what I'm hoping most of you will get from this is to understand the difference between reinforcement and matrix, and also how we can make different materials with different and improved properties. So adding the polymer to the glass meant that it's lightweight. It means that it's flexible, resistant to breaking. So you could see that in the gloves. Those gloves are not going to break, but they're quite flexible, they're lightweight, and they're waterproof. So that's why we use fiberglass. Any questions on that? So I know someone asked me to go back to this slide, but any questions? So you don't need to know the specifics. As I said, it's about just understanding the difference between a reinforcement and matrix material. Excellent. Okay, so the next thing then we're going to look at is fertilizers. So we've had a look at glass, we've had a look at ceramics, and we've had a look at composites. And that's kind of the end of the topic on different materials. As I said, you don't need to know about composites if you're not studying AQA, but it is important you understand what the difference is between glass and ceramics and why they have the brittle property that they do have. And it's all about that bonding in there. So now we're going to look at fertilizers and the importance of fertilizers. So does anyone know which key element most fertilizers contain? And for anyone that doesn't know, a fertilizer is added to plants. It helps them grow. So it's it can be a spray, so it's added to plants to help them grow. Okay, someone's given me the answer. I'll wait for a couple more people to answer. So which key element do most fertilizers contain? Good, I've had a couple of correct answers. I'll wait for some more. So this is really important. This is across all exam boards. You need to know about fertilizers. Okay, good. So the answer is nitrogen. And specifically, does anyone know in what form plants take in that nitrogen? So they don't take it in as nitrogen, they take it in as something else. So they contain nitrogen, but in what form? Not in water. What form? Not liquid nitrogen. Nope. If you've studied biology, you'll know that plants need certain things from the soil, but they don't take nitrogen in as a gas. They take it in not as a liquid, but they take it in as something else. So it comes in through the soil and they take it in as a nitrate ion. So NO3, 2 minus, the nitrate ion. So plants themselves cannot absorb nitrogen. They have to take it in as nitrate ions. So fertilizers will tend to have the nitrogen as nitrate ions so that plants can absorb them. So the next question is, why do plants need nitrate? What is it about the nitrate that plants need? What does it help plants to do? What specifically? So I've said fertilizers help them to grow, but what is it about nitrates that, what specifically do they allow plants to do? And if you think back, we did do this in a webinar where we looked at the different types of polymers in humans. And one of them was looking at nitrogen compounds and what that makes. So if you think back to that, you might know. So we were looking at natural versus synthetic polymers when we covered this, and it was a natural polymer. Not to make chlorophyll. Anyone else want to have a go? What do nitrates? Yeah, excellent. So someone has said to form proteins. Brilliant, very well done. So nitrates help plants to make proteins, and they need proteins to grow. Just like in human bodies, proteins help us to build muscle, so we need proteins as well. The webinar I was referring back to was when we were looking at amino acids, and a lot of amino acids have nitrogen in them, and that's to make proteins. So good. Okay, so they need it to make proteins. So why can't plants rely on natural supplies of nitrates in the soil? Why do we need fertilizers? Why can't plants rely on the natural supplies of nitrate in the soil? So have a think about what's different when we're referring to farming. That's where we tend to use fertilizers. Yes, brilliant. So someone is saying we remove it when we take the grown plants out of the soil. Someone's saying because plants take in nitrate via active transport, which needs energy. Okay, so you're all thinking on the right lines. So the difference between, for example, a tree or a plant that's growing in your garden is you're probably not going to uproot it or take it out. And so what happens is that plant can take in nitrates from the soil, and when it dies, it will then put that nitrate back into the soil. But when we have farming going on or harvesting, farmers will grow plants specifically then to uproot those plants when they have grown enough. And when they uproot those plants, they're essentially taking the nitrate from the soil and from the plant so that it can't go back into that soil. So the soil that the plants grow in become nitrate deficient over time. And nitrate deficient basically means there's no nitrate in there or not enough nitrate. And that's why we have to add fertilizers in. The other thing I want to talk about is nitrogen itself. So I said that plants need nitrate ions, they can't take in nitrogen. So I'm sure some of you might be thinking, well, most of our atmosphere is nitrogen, about 78% is nitrogen. So why can't they just take in that nitrogen? And it's essentially what I said before. So plants cannot take in nitrogen gas. It's not soluble. They need to take it in as a nitrate ion through their roots from the soil. And nitrogen gas itself does not dissolve in water. So they can't take it up. When we did atmospheric pollutants, you may remember me talking about nitrogen oxides or NOx. Nitrogen oxides are soluble. That's how acid rain with nitrogen dioxide in it is formed. So nitric acid, so acid rain formed from nitrogen oxide particles are formed, but nitrogen itself, without the oxygen bound to it, is not soluble. So plants cannot take in natural nitrogen from the atmosphere. They have to take it in the form of nitrates. And this process of making nitrates is called fixing nitrogen, where we make it into something that is soluble. And one of the first steps in making nitrogen that is soluble is the Haber process, where we form ammonia. So one of the first steps in forming fertilizers is the Haber process, where we form ammonia. Okay, before we go into the Haber process, any questions about fertilizers and plants? Yep, I can go over the last question again. So as I said, if you imagine plants outside, so trees and plants that you've got maybe growing in your gardens or things that you see near school, we don't tend to uproot them. So what happens is those plants and trees will take in nitrogen from the soil, or sorry, nitrates from the soil. They'll grow with them, make proteins, and then when they die in that soil and they release that nitrate back into the soil so that any new plants that grow can then use that nitrate. So it's kind of a process or a recycling process so that the soil doesn't run out of nitrate. But farmers don't grow their plants just to let them grow. They grow them so they can harvest them or uproot them to be then used as food sources. So when they grow their plants, the plants take up nitrate from the soil, but then they are uprooted so that nitrate isn't replaced. It's just taken from the soil. So the reason we need to use fertilizers is to add nitrate back into the soil. And this is only done with farmers. So you won't do this in your own gardens, for example, or outside. So they tend to have enough nitrate. Whereas when we're farming, you need to add nitrate to the soil because there's not enough, because the plants are being uprooted. And I said that process of making nitrogen soluble so that it can be absorbed by plants is called fixing nitrogen. And the first step is the Haber process, where we make ammonia from nitrogen. So I hope that helps. Okay, great. Any other questions? So it is quite complicated. So if you have any questions, don't be shy, please ask them. And that's about anything in this webinar. If you've got any questions at all, please ask. So it's only a small group of you, so please don't be shy. Okay. So the Haber process, we have touched on this before, but it's really important that we understand it. It's one of the most common things that is examined now, and that's because it tends to come up in a lot of topics. So it comes up in fertilizers, it also comes up in dynamic equilibrium, which we've covered before, and that was where we covered the Haber process, but not in as much detail. So does anyone know who this gentleman is on the screen? You should be able to get part of his name. Yep, okay, so someone has said Haber, good. So his surname is Haber. So his name is Fritz Haber, and he is the person that came up with the Haber process. So Fritz Haber. Does anyone know the raw materials for the Haber process? So I've told you one. In the previous slide, we went through one of the raw materials. So there are two raw materials. Does anyone know what they are? So the raw materials, so we want to make ammonia, so we know that's why we do the Haber process, but what are the two raw materials in making ammonia? If you know the formula for ammonia, you should be able to guess the raw materials. So someone has given me the correct answer. I'll wait for a few more answers. So what are the raw materials for the Haber process? Okay, good. So nitrogen is one of them, and the second one is hydrogen. So nitrogen and hydrogen, excellent, well done. And does anyone know the reaction equation for the Haber process? So I've deliberately not written it on the screen because we have been over it before, as I said, when we looked at dynamic equilibrium, but does anyone remember or know, it is one of the equations that you should know, that it's core and higher tier. So the reaction equation for the Haber process. So nitrogen and hydrogen makes ammonia, so that's the written equation. Someone give me, good, okay, I've seen that someone has given it to me and you are correct. So nitrogen plus hydrogen goes to ammonia. Excellent, so well done to the person that gave me that. So if you have a look, that's balanced, 2N, 2N, 6H, 2 times 3, 6H. So always make sure to balance it. And yes, these are gases, so you've guessed there. And ammonia itself is also a gas, but it can be a liquid and it can be a solid. Good. So well done to that person that gave me that. I'm very impressed. It is an equation that you should know, and it's also something that you should definitely be able to balance. So it's a common exam question. Okay, my next question is then, where does the nitrogen and hydrogen come from? So I told you where nitrogen comes from in the previous slide. I kind of touched on it. Does anyone remember, where does nitrogen and where does hydrogen come from in this process? So nitrogen and hydrogen react together to form ammonia, but where do these raw materials, this nitrogen gas and hydrogen gas, come from? So one of them is very, very abundant, which means it's very present in the atmosphere. Good. So nitrogen comes from the atmosphere. It just comes from the air outside. So remember, our atmosphere has 78% nitrogen in it. So if you go back to when we looked at the Earth's atmosphere, we looked at the pie chart of the proportion of gases in our atmosphere. The most abundant, which means the gas that makes up most of our atmosphere, is nitrogen. It's 78%. So nitrogen comes from the atmosphere or from air. And someone has told me that hydrogen comes from natural gas. Excellent. So hydrogen comes from natural gas. And anyone wondering, because I know I struggled with this at school, natural gas is actually methane, so CH4. So natural gas is methane. So well done to the person that told that just put that in the chat. So nitrogen comes from the air and hydrogen comes from natural gas, which is methane. Okay, so which conditions are used in the Haber process? Well, we have an ion catalyst and that increases the rate of the reaction. We put in a high temperature and a high pressure. And next week, we're going to be looking at why we use a high temperature and a high pressure. So it'll be a bit of a recap of dynamic equilibrium, but specifically related to the Haber process. It's called something, it's called the economics of the Haber process. So we'll be looking at that and why we use a high temperature and high pressure next week. But for now, it's just important that you know we have a high temperature, 450 degrees, and a high pressure of 200 atmospheres. Any questions on the raw materials or the reaction equation for the Haber process or what's formed? As I said, this is one of the most important chemistry topics that you will learn about. It comes up a lot. Yep, so natural gas is methane. So it is one of the fossil fuels. It's methane. So good questions. That's one of the things you can think about. Where we get hydrogen is from methane. And methane is a fossil fuel, which is a finite resource. But good question. Any other questions? Okay. So this is a diagram which I got from BBC Bitesize. I know some of you have asked me before kind of which resources I use. I tend to use BBC Bitesize for their diagrams. They tend to be quite good, and they also tend to put a lot of their content in bite-sized chunks. So if you do feel like you prefer learning from bite-sized chunks, I would definitely recommend looking at BBC Bitesize. They have recently upgraded their websites so that they now put everything by different exam boards, and I find that really useful for a lot of my students as well. So if you want to have a look at that, I would recommend it. So let's have a look at this diagram then. This is looking at how we make ammonia from nitrogen and hydrogen. So we said nitrogen is from the air and hydrogen is from methane or natural gas. So they go in and then they have this compression. Any ideas what the compression does? Why do they go into a compressor? What's the function of that? Any ideas? They go into a compression chamber. So what does compression mean? So someone said puts them together, not quite. Someone said makes them more dense, not quite. So compression means kind of pushing. Good, pressure. So someone has said pressure. So when we put them in a compression chamber, we're increasing the pressure. So remember I said that one of the key kind of requirements for the Haber process is a high pressure. So we put it at 200 atmospheres and that's the high pressure. So it happens in a compression chamber where we just basically squeeze and basically increase the pressure in that chamber. They then, which have a high temperature added to them, so you can assume in that compressor there's also a high temperature. I know it's not on the diagram, but it is there. There's high temperature and 200 atmospheres. Okay, and then we follow the arrows and we end up here in the ion catalyst beds. So remember, the ion is a catalyst. A catalyst speeds up the rate of reaction without being used up itself. So again, that was something we looked at when we looked at rates of reaction and equilibrium. So catalysts do not get used up, but they speed up the rate of reaction. Does anyone remember how a catalyst speeds up the rate of reaction in terms of the activation energy? Anyone remember? It's a good recap of rates of reactions. So how does a catalyst speed up a rate of reaction? Good, so it doesn't quite lower the activation energy. It provides an alternative route with a lower activation energy. So you'll remember that most reactions require some energy to allow the reactants to react together to form a product. If we add a catalyst in, it doesn't lower the activation energy, it finds a different route for the reaction or an alternative route, and that route has a lower activation energy. So it's really important when you're answering exam questions about catalysts, you don't say they lower the activation energy, you say they provide an alternative route for the reaction with a lower activation energy. Good, okay, so they go through this catalyst that speeds up the rate of the reaction. And then you get nitrogen, hydrogen, and ammonia coming out. And what we can see happening is the nitrogen and hydrogen is actually recycled. So any nitrogen and hydrogen that didn't react together then goes back in. So it's recycled. So that's a good process so that nothing is wasted. And then the ammonia that comes out is cooled. Why do we cool the ammonia? What does that allow the ammonia to do? Does anyone know? It's kind of on the diagram. But what does the ammonia allow, or what does the cooling tank allow the ammonia to do? It's quite an important part of the process. So have a look here, what this says. What does the cooling tank allow the ammonia to do? Good, so it basically, you have a gas, so ammonia comes out as a gas like nitrogen and hydrogen, and the cooling tank basically changes the gas into a liquid. So what's the process of something going from a gas to a liquid called? Condensation. Excellent. So from a liquid, from a gas to a liquid is known as condensation, and that's what happens when we get liquid in ammonia and ammonia comes out. Okay, any questions then on the process or the Haber process and what happens? So it's quite important that you understand that. Common exam question. Okay then, I don't think we've got any questions on the Haber process. If you do have any on any of today's content, please do ask. So before we look at some exam questions, let's just recap everything we've kind of looked at today. So we looked at the physical properties of glass and ceramics. So remember, they are both brittle, and that is because of the ionic and covalent bonding. When we strike it, it can be broken and we can cause repulsion in those within the ions, and that makes the glass and the ceramics break. And that's why we use composites. So composites are two or more materials bound together, and they tend to have improved properties. So the example I gave was glass and ceramic. That stops it being brittle. We looked at fiberglass, which is flexible, lightweight. We looked at reinforced concrete, which we use in bridges and things, and that makes them tough. It resists the bending forces that concrete tends to have. And we looked at carbon reinforced polymers. Again, they will conduct electricity, they'll be lightweight and tough. We then looked at the uses of nitrogen-based fertilizers. So first of all, fertilizers will contain nitrogen in them, specifically nitrates, and plants need nitrates to make proteins and to help them to grow. And why we need to add fertilizers is because the soil does not have enough nitrate in it. So we add nitrate to it because when farmers grow plants, they uproot them. So they remove any nitrate when they uproot that plant. So they have to keep re-adding that nitrogen back in. The first part of making a nitrogen-based fertilizer is actually changing nitrogen in the atmosphere, which is insoluble, into ammonia, which is known as the Haber process. And we do that using nitrogen and hydrogen, which are the raw materials. Nitrogen comes from the air. Remember, 78% of the atmosphere is nitrogen, and hydrogen comes from methane or natural gas. So the same thing, and they bind together in the Haber process to form ammonia. And that is the first step in making a fertilizer. And we'll be looking more at making fertilizers next week once we've looked at the economics of the Haber process. Okay, so let's do some exam questions. Okay, so a flow diagram of the Haber process is shown below. The Haber process produces ammonia from nitrogen and hydrogen. Where does hydrogen come from? And just to say, when I was looking for exam questions for this topic, the Haber process has so many exam questions and they are all really, really similar. Yep, so natural gas, well done. So I just want to point out that this is a really common topic to be examined on because it's so easy to be examined on it, and examiners like to look at this topic. It's very, very common, so I would definitely recommend understanding it really well. In the reactor, nitrogen and hydrogen at a high pressure are heated and passed over a catalyst. What's the temperature? Does anyone remember which temperature I showed on the screen? Good, 450 degrees, excellent, yep, so 450 degrees. And for anyone wondering why, we will be looking at that next week. So hold any questions that you have. Which catalyst is used in the reactor? Good, yep, iron. And again, we'll be looking at why we use a catalyst next week, but we've kind of touched on it today. Good. Okay, so how does a gas speed up how does a catalyst speed up a reaction? So they've given the answer that you shouldn't give if you're writing an answer. Yeah, it lowers the activation energy. So it does lower the activation energy, but it finds an alternative route. So this is an older exam question, but the newer exam boards now want you to say that it finds an alternative route, which has a lower activation energy. Okay, a mixture of gases leaves the reactor. The mixture contains ammonia, nitrogen, and hydrogen. Describe what happens to this mixture of gases in the condenser. So the last part of the Haber process, there were two things that happened. So what happens to the ammonia and what happens to the nitrogen and hydrogen? There's 3 marks. Good, so the ammonia goes from a gas to a liquid, so it's condensed and comes out as a liquid, so that gives you 2 marks. So you need to say the ammonia is condensed to form a liquid. Good. And then what happens to the nitrogen and hydrogen? Good, yeah, so they are recycled. So the nitrogen and hydrogen are recycled and they go back to the iron rods, which is excellent. So for anyone confused about that, if I just show you this diagram again. So this question is asking about this last process here, where you've got nitrogen, hydrogen and ammonia coming out. The nitrogen and hydrogen goes back, cycles round so that it could be reused or recycled. So any nitrogen and hydrogen that hasn't reacted together is then given another chance, so it's recycled. And then the ammonia comes out as a gas, and in the cooling tank, it liquefies or condenses so that we get liquid ammonia coming out. So we can't use ammonia as a gas, and as well, it might escape. So we want it as liquid ammonia. Good. Okay, let's go to the next question. Where does the nitrogen used in the Haber process come from? Again, loads and loads of questions on the Haber process. Yep, so nitrogen comes from the air around us. Good. Okay, this is a question kind of reminding us about rates of reactions. So does anyone remember? A high temperature of 450 degrees is used in the reactor. Why do high temperatures make reactions faster? So do the particles move faster? Are they closer together? Do they collide more often? And do they have less energy? So what is it about having a high temperature that makes the reaction faster? So there's 2 answers. Good, excellent. So the particles move faster and they collide more often. So it's not about them being closer together. Good question. So if you remember when we looked at rates of reactions, when we increase the pressure, we move the particles closer together. So pressure will move particles closer together because pressure is almost about squeezing a container, making it smaller and smaller. And that basically moves the particles closer together. But when we increase the temperature, we're not changing the pressure in there. we're giving the particles more energy, so they move faster. And if they move faster, they're more likely to collide. And remember that reactions happen when particles collide with enough energy, which is the activation energy. But good. If you're confused on that at all, again, we've got a webinar on YouTube looking at the rates of reactions, which I did a couple of weeks ago. But hopefully we'll be looking at it in a bit of detail next week when we look at the economics of the Haber process. So for anyone that didn't get that, so particles move faster and they collide more often. Okay, just before we finish then, I said that there are no questions on composites, and I'm right, there aren't, because it's a very new topic, but there are a couple of questions on glass. So I thought we'd just have a look at this. So the table below gives information about milk bottles. So specifically a question about a glass milk bottle and a plastic milk bottle. And this question is asking us to evaluate the production and use of bottles made from soda lime glass and those made from polyethylene, so the plastic. So you want to justify your choice of material. So what are the advantages and disadvantages of using glass versus polymer? So let's have a think and look at this table and also what we know. So does anyone remember how many steps are there to make glass? How many steps in the process of making glass? 2, good. So it's melting and cooling. Okay, what about plastic? How many steps are there to make polyethylene? And I'll be really impressed if you can name the steps as well. So we've covered this before, but does anyone remember how many steps to make polyethylene? So it's a polymer. So there are 2 steps to make glass, heating and cooling. How many steps to make polyethylene, which is a polymer? Don't worry if you get it wrong, but if you can name any of the processes, that would be really great. Someone's asking, do catalysts increase the pressure? No, they find an alternative route for the reaction that lowers the activation energy, so they have no impact on the pressure. Okay, so no one has answered what the steps are in making a plastic milk bottle. That's fine. So the first step is to use crude oil, and we do fractional distillation. So hopefully some of you remember what fractional distillation is. The next step is cracking to make smaller alkanes and alkenes. And hopefully you remember that a polymer is made from ethene bound together. So we have to do polymerization. So the steps to making polyethylene, there are 3. So what I'm getting at here is the difference between a glass and a plastic milk bottle, or some way of answering this question about evaluating these bottles is to say, for example, that a bottle made from soda lime glass has fewer steps in it, when the plastic milk bottle has more steps in it, so it's more of a lengthy process, requires more time and potentially more manpower. We can look at the temperature, for example. So the soda lime glass requires 1600 degrees, whereas the plastic only requires 850 degrees. So you could say that a disadvantage of the glass milk bottle is that it requires more energy. And where does energy come from? Greenhouse gases are produced from the fossil fuels when we burn them. We can look at the number of times that a bottle can be used. So you can see that glass can be used 25 times, which means that it can be used a lot more, whereas a plastic bottle can only be used once. So it can't really be recycled. It means then that we use it once and that's it. So actually maybe using glass is better. It can be reused. Is that better for the environment? So things like that are kind of points you can make when answering this question, looking at evaluating the production and use of bottles made from soda lime glass and those made from polyethylene. Any questions on that question at all? So I was just trying to help you to come up with different points that you could say. I would definitely recommend having a go at this question in your own time and using the table, because there's lots of different points you can make, and also points you know about making plastics versus making glass. Okay, well done today, everyone. You all did a really great job, and you were also really engaged, which is excellent. As I said, next week we'll be looking at the economics of the Haber process, so looking at why we use a high temperature and a high pressure. So it's a bit of a recap on rates of reactions and the economics of the Haber process. I look forward to seeing you all next week. Have a lovely week. Take care of yourselves. Bye.